All right, so we've learned about the first derivative test and what it can tell us about our function. Now we're going to talk about the second derivative and what the second derivative tells us about our function. So the first thing that we're going to talk about in this video is concavity. So if you think about back to like algebra, you learned about what concave up meant and what concave down meant. So, you know, a little visual mnemonic device here. Concave up is like a smiley face because we love calculus. Concave up is like a smiley face, and concave down is like a frowny face. So concave up, concave down, that's sometimes maybe just how you have to remember it. So let's look at what that looks like and what the derivative is doing at those points. So here's a function. It's concave up. And what is actually happening with the tangent line there? So we can see they've got some tangent lines drawn, and what you can see is like figure out the slope of this tangent line. I don't know, like -1, let's say. So it's like -1 is maybe the slope of that tangent line. And then if we drew another tangent line, slope of that one is like -2/3. And then we draw another tangent line, and that was maybe like -1/4. And then we draw another tangent line, and that one's like maybe 1/4 is the slope. You see how it's getting positive now. And then maybe this one's 1. Then we draw another tangent line. And maybe the slope of that one is like 3/2. So what's happening to the slope of the tangent line? What's happening with the derivative? Well, it keeps getting bigger, right? It starts here, and it just keeps getting bigger. Those are just bigger and bigger and bigger numbers, which means that the derivative is increasing. Okay? So when we're concave up, the derivative is increasing. So what does that mean for the rest of the function, or for the f double prime? So if the first derivative is increasing, well, if we think back to our first derivative test, the derivative is positive when the function is increasing, right? So if we think of the second derivative, it's the derivative of the derivative, right? So when the second derivative is positive, then the first derivative is increasing. And when the first derivative is increasing, the second derivative is positive. Therefore, when the second derivative is positive, our function, our actual function, f of x, is concave up. So that's the second derivative test for concavity. If the second derivative is positive, then f, our actual function, is concave up. So if you look at this, the other thing that you can notice is that you see that the tangent lines are always below the graph. That's how you can tell that it's concave up, and so sometimes it's hard to actually figure this out on certain functions. It's hard to see where it switches concavity. So draw a tangent line and figure out if it's below or above the graph. See, because if I drew this tangent line above the graph, like right here, and tried to touch that, do you see it would cross the function more than once, right? So then it wouldn't be a tangent line anymore, it would be a secant line. So if I tried to draw any tangent lines inside the function, it wouldn't work because they would cross over a couple times. So tangent lines are below the graph, we're concave up. So the opposite is also true. So a graph that is concave down, the tangent lines are above the graph. See how the tangent lines are all outside the graph on the top? And if you can think about, again, let's look at these slopes. Well, this slope is, say, like, I don't know, 1, and then we go to like 1/2, and then we go to 0, and we go to -1/2, and then we go to -1. So that as we figure out the slopes of each of these tangent lines, the slope of the tangent line, which is the derivative of the function, so the derivative is decreasing. And if a function is decreasing, then its derivative, which in this case would be the second derivative, is negative. So we can decide that if the second derivative is negative, then f of x must be concave down. So let's look what that looks like on a graph. Oh yes, a point of inflection. So on a graph, a point of inflection is where the graph changes concavity. The graph has to have a tangent line at that point, so it has to be differentiable at that point, and it's where it changes concavity. So if we look at this one, you see how this is concave down, concave down, concave down, concave down, and then at this point right here, it's now concave up. And the way you can do that is we can look at the tangent lines, okay? So these tangent lines are above the graph, right? Every point here has a tangent line that's above the graph. And then when we get over here, the tangent lines are below the graph. That makes it concave down, or concave up. That's not confusing. Okay, so this point right here is a point of inflection at 0, 0. So let's take a look at a graph really quick and see if we can analyze it for concavity. So we're going to use this graph to answer some questions, and we're just going to look at the graph. Okay, we're not going to do an actual function right this second. That comes in the next video. So on what intervals is the graph concave upward? So again, if we can see that it's kind of like concave upward here, and it's kind of concave upward here, and it's kind of concave upward here. So we just think about, like, where does it look like a smiley face, right? And if you really need, if you're not sure, and you need really reassurance that this really is concave upward, you can look at the slope of the tangent line and see that the tangent lines are underneath the graph on all of these. Maybe one day I'll get really good at writing on tablet. We'll see. Those don't look great. Okay, but see how the slope of the tangent line on all of those, or the tangent lines, excuse me, are underneath the graph. So this graph is concave upward from -2 to -1. Oop, on the wrong one. And then it's also concave upward from 1 to 3. And then it's also concave upward from 4 to 5. So where is it concave downward? Well, it is concave downward from -1 to 1. And from 5 to 6. And then we have a couple of spots, and you might not be able to see this on the thing very well, but we have a couple of spots where it doesn't seem to be curving at all. In fact, in this spot right here, you see how it's just like a line? And here is a line as well. So what's going on there? Is it concave up or is it concave down? Well, a line has no concavity, okay, because a line is straight. So any straight line has no concavity. We're only talking about like curves when we talk about concavity. So the next question is, on what intervals does the graph have no concavity? Well, that would be from 3 to 4 and 6 to 7. So then we're asked, what are the points of inflection? Well, we know that a point of inflection has to meet two requirements, right? It has to have a tangent line, which means f prime has to exist, and it is where the graph changes concavity. So let's look at our graph. Okay, I can't spell concavity. Wow. Okay, concavity. Okay, so where does the derivative exist, and where does it change concavity? Okay, so we change concavity anywhere it changes from blue to red, right? So changes from blue to red right here. Is that a point of inflection? No, because the derivative does not exist at this point. See, you couldn't draw a tangent line here because it's a sharp curve. So the derivative does not exist at that point, therefore that is not a point of inflection. Now we go here and it changes right here again from red to blue. Is that a point of inflection? Yes, it is, because the derivative exists. We could draw a tangent line right there. So our first point of inflection would be 1, 1. And then let's look at some more. It changes from blue to yellow right here. Is that a point of inflection? Well, no, it's not, because it doesn't actually change concavity, because it doesn't change from like concave up to concave down. It just stops having concavity at all, so it doesn't count. So then right here, again, not a point of inflection because the derivative does not exist. Then we come here, and now it changes from blue, which is concave up, to red, which is concave down. Is this a point of inflection? Well, does f prime exist? Could I draw a tangent line right there? I sure could. That would work. Right there, I could draw a tangent line. So f prime exists at that place, so that is our other point of inflection at 5, 1.